Hello. So today what I'd like to do is to speak to you a little bit about acids and bases. So I'm going to do a little bit of work on discussing a few of the ALEKS problems on acids and bases. Again, feel free to refer to earlier recordings on this topic. There's more videos that you can watch on acids and bases posted on YouTube, but also posted in the announcements on Blackboard. Okay. So let's talk about acids and bases. Acids and bases, we've heard those terms before. They're important for many reasons, but one reason has to do with the idea of water. Water, of course, is essential for life. Life evolved on the earth in water, most likely. Water is important in all sorts of metabolic processes within organisms. It's a central component of the earth. It even affects the properties of the earth itself. Okay, so one thing we can do is we can think of water as really being comprised of two different species. This is one way to visualize it, to think of a water as two separate ions that are just combined together. H plus, the hydrogen ion, and sometimes this is referred to as a proton because a hydrogen atom has one proton and one electron, typically. If you take the electron away, you're only left with the proton, and that's what a hydrogen ion appears to be. It's just a hydrogen atom without its electron. So it would essentially be a proton. And this is called the hydroxide ion. Now, in practice, this is a relatively rare occurrence. The water molecule does not easily get converted into a hydrogen ion and a hydroxide ion. However, there is evidence to suggest that water molecules can react with each other. And when that happens, what happens is one of the hydrogens is transferred from one water to the other water. So the first one loses a hydrogen ion, not a hydrogen atom, but a hydrogen ion. And by losing the hydrogen ion, you're left with the hydroxide ion. And the other water picks up that hydrogen ion. So it's a transfer of that hydrogen ion, right? So let me draw a little arrow here. It's one of the hydrogen ions is being transferred to the other water. Now this is called the hydronium ion. And although there's not much evidence for the existence of a hydrogen ion and a hydroxide ion in water, there is some evidence for the hydroxide ion and the hydronium ion. There's more evidence for that. So this is not a bad way to think of those two species. They're the products of the reaction of water with itself, which is called autohydrolysis. Auto means with the same, and hydrolysis means reaction with water. So really what it's saying is water is reacting with itself, right? And so you get these two ions. These two ions, you should know them. OH negative is the hydroxide ion. H3O plus is the hydronium ion. And that leads us into one way of thinking about what acids and bases are. So an acid is a substance that produces the hydronium ion, which is H3O plus, in water. Okay. So if something produces the hydronium ion, it's considered an acid. So you might ask, well, wait a minute. These two water molecules, they reacted to form a hydronium ion. So does that mean that the water molecule is an acid? And the answer is yes. What that means is essentially water is an acid. It does behave like an acid under some circumstances. If you produce the hydronium ion, you're an acid. Now bases, it's the same idea, it's just the hydroxide. So a substance that produces a hydroxide ion. In water. Okay. So then you might say, well, wait a minute, we got the hydroxide out of that too. So does that mean it's a base? And the answer is yes. In fact, one of those two species of water is acting as an acid and the other one's acting like a base. Okay. Producing a hydroxide base, producing a hydronium acid. Okay. Water is said to be amphiprotic, like amphibian, proton. So amphibian, if you think about what an amphibian is, like a frog, right? A frog, part of its development is in the water and part of it's on land, right? That's what amphibians are. Amphiprotic, similar. It's acting like an acid and it's acting like a base. The protic meaning the hydrogen ion. Okay. So water is an amphiprotic species. So what are some examples of these acids and of these bases? I want to go over just a few. So some examples. Let's start with the acids. So the first one are the inorganic acids like HF, HCl, HBr, and HI. Okay, so those are four common examples of acids. Notice the format: hydrogen, halogen, right? Fluorine, chlorine, bromine, and iodine are in group 7A. So if you combine one of the halides with a hydrogen ion, you have what's called a hydrohalic acid. So these are called hydrohalic for halogens acids. And typically there are four of them. The naming for the hydrohalic acid is relatively simple. You just put hydro at the beginning, and then you name the nonmetal and put ic acid at the end. So fluorine becomes fluoric acid. Hydro, so you put hydro at the front, and then you change the name of the element from chlorine to chloric. Same thing here. Hydro, bromine becomes bromic acid. Hydro, iodine becomes iodic acid. Okay, so those are the names of the hydrohalic acids. We can write them as undergoing a reaction in water. So I'm going to write it aqueous. Acids are generally soluble in water, so I'll write aqueous next to them. There are some examples of organic acids that are not soluble in water, but generally they're pretty soluble. So we can write them as what we call dissociation or ionization. Okay, dissociation or ionization, why would we call it that? Dissociate means to break up. So the HF is breaking up into H plus and F minus. So notice you got that hydrogen ion there, right? So that means it's an acid. Anything that produces H plus in water is considered an acid. So this is called dissociation. Or it's also called ionization because you're forming ions, right? So in general, acids are considered molecular substances, but they form ions. So that's kind of interesting, right? Wait a minute. Didn't we say that substances that form ions are ionic compounds? Well, yes, but in general, acids are considered molecular substances. Okay. All right. Now we can write this in a slightly modified form. Instead of writing it as just dissociation, I'm going to write it as a reaction. So remember, this is occurring in water. So we're putting this hydrofluoric acid into water. What we're going to claim is that if it's an acid, it can donate or transfer the H plus to the water. So you'll get F minus And then again, if you take water and you add an H plus to it, you get H3O plus, which is our hydronium ion, right? This is just a different way of writing the same process. We either think of it as dissociation and ionization, or we think of it as a proton transfer. So the hydrogen ion is being transferred, the proton is being transferred from the fluorine ion to the water molecule. So in that case, we would think of the HF as an acid because it's producing a hydronium ion in the water. Okay. So those are acids. Those are 4 of them. There are also a much larger group of acids, which we call the oxoacids. And the oxoacids have oxygen. These are oxygen-containing acids. Pretty cool. And there's a lot of them out there. So I'm just going to give you a list of some of them. In general, the format is you have a hydrogen, or maybe more than one hydrogen. Then you have a nonmetal. Then you have some number of oxygens. So here's one example: H, hydrogen, nonmetal, Cl, and then oxygen. And often what can happen is the number of oxygens can vary depending on what the substance is. So it turns out there's another one very similar, except that it has 2 oxygens. And there's even a couple of others, 3 oxygens and 4 oxygens. Okay. Now, because there can be more than one acid with the same nonmetal, just varies the number of oxygen atoms. We have to have different names for them. So in general, the way it works is if the polyatomic ion that's in the acid, that's ClO2 minus, right? Because H is H plus. That is called the chlorite ion. And if the name of the polyatomic ion is ite, the name of the acid is us acid. So this one is called not chlorite, but chlorus acid. Okay, so ite goes to us acid. Okay, the ite is the ClO2 negative. That's the polyatomic ion. The polyatomic ion, if it ends in ite, it gets changed to us acid by putting the H plus on it. So you're thinking of the acid as having 2 parts. It's a binary substance. It's got the hydrogen ion and then the nonmetal ion. Okay. Now, if it has one more oxygen, then the name of the polyatomic ion is 8. So this would be chlorate with the 3 oxygens. So you change 8 into ic acid. So this would be called chloric acid. And that's based on the idea that 8 is turned into ic acid. Okay. And for many acids, there's 2. There's the us acid containing the ite polyatomic ion, and there's the ic acid. I wrote chloric twice, I'm sorry. And then there's the 8 polyatomic ion, which is called ic acid. Notice no hydro at the beginning. The oxoacids don't have hydro at the beginning, only the hydrohalic acids. Those ones are the ones that are going to have the hydro at the end. There's some other hydro as well, but the oxygen-containing acids don't have the hydro at the beginning. But there are a few where there's 4, like 1 oxygen, 2 oxygen, 3 oxygen, 4 oxygen. So we have to have names for those. So what we do is we say, well, look, if it's chlorous acid, but you take away 1 more, that's less than 2. It only has 1. So we put hypo at the beginning. So this is called hypochlorous acid because it has less than 2 oxygens, less than the chlorous acid does. And if it has 1 more, we call that per, as in hyper, more than. So this is called perchloric acid. Okay, so if there are 4, which is what you get. There's 4 different possibilities when you have a halogen with oxygens. You can have HClO all the way through HClO4. It's hypochlorous, chlorous, chloric, and then perchloric. But generally, most of the oxoacids only have 2 possible. So the 2, if it only has 2, then you just do these 2, the us and the ic. So there's a group of 4. Let me show you another set. Okay, so there is no H2SO5, and there's no H2SO2, and there's no H2SO that we need to worry about. So this one has fewer oxygens. So the name of the polyatomic ion is sulfite, right? So that's sulfite. And what we said was sulfite is going to go to sulfurous acid. And so that's the name, sulfurous acid, right? Ite goes to us acid. And then this one has 1 more oxygen, so it's sulfate. That's the name of the polyatomic ion. So the acid is called sulfuric acid, okay? So there's more examples of these where there's only 2 possibilities than there are where there's 4. So here's another example. H3PO3, H3PO4. Okay, so this is phosphite. So it's phosphorus acid. Oops, I misspelled acid. And then you've got phosphate. So it's phosphoric, right? 8 goes to ic acid, and then ite goes to us acid. So there's a bunch of examples like that. Okay. And there you go. So there's 2 general patterns here. One is hydrogen with a nonmetal, and then hydrogen with a nonmetal and then some number of oxygens, okay? Now you'll notice, see how this one has 2 hydrogens and this one has 3? Those occur. There are acids with 2 hydrogens, there's acids with 3 hydrogens. We go more in detail, more in depth into that in the next course, Chemistry 1200, if you're interested. But in general, if there are 2 hydrogens or 3, we call them polyprotic acids. So polyprotic acids are the ones where there's more than 1 hydrogen in the acid. Okay, so there's your acids. Now let's talk about bases. There's 2 groups of bases that we want to be concerned with. The first one are the metal hydroxides. And so those would be lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium, and cesium, Cs. So you'll notice all of those metals are group 1A metals. So it's a group 1A metal with 1 hydroxide. Now these are ionic compounds. They're not molecular, they're ionic. What they will do is they will just dissolve in water to form ions. Okay, same thing here. Na plus OH minus, so forth and so on. Now, the naming for these is there's no changing of the names for it. You just name it just like a regular ionic compound. So this would be called lithium hydroxide. And the lithium and the group 1A metals will combine them with hydroxide. They combine in a 1-to-1 ratio because of the charges. Okay, so there's a few. The other ones, another list of these include magnesium. But this one, because magnesium has a charge of +2, it actually has 2 hydroxides. Calcium strontium, barium. Okay, these ones, again, they're just ionic compounds, but they form two hydroxides. Okay, so magnesium hydroxide would be the name of that base. It's an ionic compound, but it's also a base. It forms a magnesium ion and two hydroxides. Okay, and there is the first group of bases, the ionic bases, the ionic compound bases, group 1A and group 2A. Now, sometimes people will include beryllium because it's also in group 2A. Sometimes they don't. It just depends. Magnesium is what we call a weak base, magnesium hydroxide, because it's not very soluble in water. So if it's not that soluble, it can't really produce that much hydroxide. It is slightly basic. It is a base, but because it's not that soluble, it doesn't form a lot of hydroxide in the water. The other ones are soluble in water though, so they produce quite a bit. In fact, these ones produce more hydroxide than these ones do, because look, there's two of them. There's twice as many hydroxides in the formula. Okay. Now that's all really one group, the ionic compounds, right, that are bases. Group 1A hydroxide with one hydroxide, group 2A metal with two hydroxides. Other substances like aluminum or zinc or iron, combine them with hydroxide, they're not bases because they're not soluble. Hydroxide salts are generally not very soluble in water. And so if you have aluminum or iron or chromium combined with hydroxide, you're just not going to get enough solubility to produce any significant amount of hydroxide in the water. So those are the, really it looks like 9 of the strong bases. We might call them strong bases or ionic bases. Now, there is another group that we have to be aware of, particularly those that are biology and those majors, and those are the nitrogen bases. And these ones are, the first one is ammonia. It's NH3, and it doesn't, you look at it and you say, well, wait a minute, how can that be a base? There's no hydroxide in it. And it just has to do with the peculiarities of this substance. It does dissolve in water really well. You have ammonia-based cleaners. It will react with water. And what will happen is the water will transfer an H+, one of its H pluses to the ammonia, and you get an NH4+. Remember, ions are soluble in water. Now, when the water transfers the H+, it becomes OH-. So this is called the ammonium ion. And then this is called the hydroxide ion. So why is it a base? Remember what we said at the beginning. A base is something that produces a hydroxide in water. So if you put the ammonia in the water, it will react with the water and produce hydroxide ions. So that's considered a base. So this is why we call them nitrogen bases, because they tend to be of the format nitrogen with some number of hydrogens, maybe 1, maybe 2, maybe 3, okay? But they might also just have maybe 2 and then some organic component like CH3 or something like that, right? So if you see a nitrogen and it's bonded to a carbon or bonded to a hydrogen, so NC or NH, then it's a nitrogen base. Okay, doesn't matter how many carbons, doesn't matter how many hydrogens. If it's a nitrogen bonded to either carbon or to nitrogen, or I'm sorry, to hydrogen, then it's a base. So here's an example. This is a carbon ring, NH2. This is called aniline. So when you see this little ring, see that ring there? Really what that's saying is you've got carbons at each point in that ring. Okay, so there's your 6 carbons. And then we're not going to talk about bonding, what that little circle means. It has to do with chemical bonding. We'll get later in the course, we'll get into that. But essentially what happens with aniline is each carbon has one hydrogen. And then this one has the NH2. And so there's your NH2, right? So that's an NH or an NC. So that is definitely a base. So aniline is a base. Okay. The substances that you've heard of that are nitrogen bases, some of them, caffeine, morphine, nicotine, cocaine, heroin. Okay. All of those are what we call nitrogen examples of nitrogen bases. Okay. They have in their structure, they are organic molecules with carbon and hydrogen. Somewhere in there is a nitrogen atom, and that nitrogen is either bonded to one or more hydrogens, or it's bonded to a carbon or both. Okay, so you got two very different types of bases, right? You got the ones with the metal hydroxide, those are obvious bases, group 1A, group 2A, but now you also have these nitrogen bases, and we won't go into too much more detail than that. Okay, so what I want to do is I want to spend a little bit of time showing you an example or two of the Alex problems. Hopefully that's all right there. And so here's one, identifying acids and bases by their chemical formulas. That makes sense, right? So look at the first one, H3PO3. Well, that's the phosphorus acid that we went over, right? But see, it's got the hydrogens and then a nonmetal and then oxygens. So that's a molecular acid, right? We only really looked at molecular acids. We didn't look at ionic acids in here, but we did look at ionic bases and molecular bases. The nitrogen bases are molecular bases, and the group 1A or group 2A bases are the ionic bases. Second one, H3PO4. Oh, same as the first one, H3PO4. You've got a hydrogen or more than one hydrogen, a non-metal, and then oxygens. So that's a molecular acid. So you would check both of those. HF. Oh, there we go. Hydrogen and a non-metal. That's an acid. So molecular acid. So molecular acid. KF. Oh, there you go. KF. Non-metal. I'm sorry, metal. Non-metal, but no, remember the ionic bases have the hydroxide in them, like KOH. This doesn't have the OH, so it's not an ionic base. It doesn't have a hydrogen, so it's not an acid to begin with. So it doesn't look like it's either of those. It's just an ionic compound. So we just write here ionic, right? Potassium is a metal, fluoride is a non-metal, so that's just an ionic compound. Show you one more. First one, second one, and the fourth one are all the same. Hydrogen, non-metal, oxygen, hydrogen, non-metal, oxygen, hydrogen, non-metal, oxygen. So those are all molecular acids. The third one, however, has a metal with a non-metal. There's no hydroxide in there, so it is ionic, but it's not a base. Okay, so there you go. Close that one. Let's take a look at a different problem. Predicting the products of a neutralization reaction. Predict the products of the reaction below. That is, complete the right-hand side of the chemical equation. Be sure your equation is balanced, okay? So here we're just predicting the products of the reaction. So notice we have an acid here, HClO3, right? Hydrogen with a polyatomic ion. That's the chlorate ion. Here we have a metal with hydroxides. It's a group 2 metal, so that's a base. So it's an acid-base reaction. Now here is how we deal with, very often this is how we deal with acid-base reactions. Let me show you right here. We think of these acid-base reactions as what we call double displacement. Now, sometimes it's called double replacement. Just depends who's writing it up, okay? But essentially what we do is we think of the acid as having two parts. And the two parts are H plus and ClO3 minus. So see how I'm putting brackets around them just to kind of separate them? Internally, think of it as having two parts, the H plus and the ClO3 minus. The same is true with the base. In this case, the base is calcium hydroxide. So that's an ionic base, right? So think of this as having two parts. Don't worry that there's two of them in there for now. We'll deal with that in terms of balancing the equation. But for right now, just think of, well, you can write it like this if you want. Right? It's Ca plus 2 and then 2 of the OH minus attached to it. Okay. A double replacement is generally the following. You have a positive and then a negative reacting with a positive and a negative. Right? Positive, negative. They switch partners. The first positive goes with the second negative. So you get M plus Y negative. And then the second positive goes with the first negative. So you get N plus X minus. So do you see why we might call that double replacement or double displacement? They're displacing each other, replacing each other. Switching partners is one way to look at it. They're just switching partners. So that's what we'll do. That'll be our approach for acid-base reactions for many examples, is we just switch partners. Okay. So H plus is going to go with OH minus. Now, what's H plus and OH minus? H2O, right? And then the Ca plus 2 is going to go to the ClO3 minus. But now we have to be very careful with charge. Remember, this one's 2 plus and this is 1 minus. So we need 2 of these. You need 2 of the ClO3 minuses to balance the plus 2 charge. So we put it in parentheses because it's a polyatomic ion. And then I'm going to put the states of matter in here. Water is generally written as a liquid because it is the solvent and it's a liquid. And then the other substance is just going to be aqueous because it's made up of these ions. Now, if it's insoluble, if it's a precipitate, then we would put S for solid. But most of these examples, it'll be aqueous. Okay, now we can balance it. And here's how I would balance it. What you do is you look at the counter ions, the polyatomic ions. See how you've got 1 here, but 2 there? So put a 2 here so that you got 2 of those polyatomic ions. Then take a look and see how you've got 2 of the hydroxides here. Remember, water is H plus OH minus. You can think of it as H plus OH minus. So if you have 1 water, you have 1 OH minus. Here we've got 2 OH minuses. So I'm going to put a 2 there. And now you've got your balanced equation. Pretty cool, right? Let's do another one. Predicting the products of a neutral. Neutralization is a term we use. It has multiple meanings, but in this context, it means an acid-base reaction. We're neutralizing the acid with a base. But that's generally, in this context, that's what that means. Predict, and actually they use that in, like when you look at like Tums or Rolaids, they talk about neutralization, neutralizing power, right? Predict the products of the reaction below. So the format's the same, H plus ClO3 minus, so plus minus, NaOH plus minus. We're going to do this as a double replacement. Do the right side of the equation and then balance it, okay? Okay, so we have H, ClO3, plus NaOH. Okay, now just to do the extra step, what I'm going to do is I'm going to remind us this really has two parts. Two parts. Right? Two parts for each one. You got the acid and the base. Okay, switch partners. The H plus is going to go with the OH minus. That gives you water. The Na plus, we generally want to write the metal first, the cation first, and then the ClO3 minus. And again, write that as aqueous. Now this one's already balanced. You can check it, but it's already balanced. We don't have to worry about having more than one polyatomic ion there. Okay, so you got your balanced equation. There you go. There's another neutralization or acid-base reaction. I'm going to do one more. HNO3 plus BaOH2. Okay, so there's your acid, right? You recognize that as an acid. Now, see how it's a nitrogen? Let's see if we can figure out what the name of this one is. It has oxygen, so it's not going to have the hydro at the beginning. So it's nitrogen. So but then it turns out this one has 3 oxygens. With 3, it's nitrate. That's the polyatomic ion, nitrate. And remember what we said? 8 goes to ic acid, so nitric acid. If it had had 2 oxygens, it would be nitrite, so that would be nitrous acid. So this is nitric acid. Group 2 metal, make sure you have your periodic table. You'll see barium's in group 2A with hydroxide. So that's barium hydroxide. That's an ionic compound and the base. Okay, double displacement. So HNO3 plus BaOH2. Okay, H plus NO3 minus, right? Acids can generally be thought of as an H plus combined with a polyatomic ion or a monatomic ion like fluoride, chloride, bromide, or iodide. Here's your barium, group 2A, so it's +2. And then you got the 2 hydroxides, so I'll write them like this. Okay. So now, excuse me, what do? Switch partners. The H plus is going to go with the OH minus. Now here's another way to think about balancing it, just to kind of save yourself some time. See how there's 2 hydroxides here? So we need 2 H pluses. So I'm going to put a 2 here. So now you got 2 H pluses and 2 OH minus. That's going to give you 2 waters, right? So if it's the case that H plus plus OH minus gives you water, and it's also going to be the case that 2H plus plus 2H minus is going to give you 2 waters. And that's exactly what we have right here. Okay. So we balance that part. Now what about the barium? The barium is going to go with the nitrate. Again, you want to put the metal first. It's a polyatomic ion. Now we may recognize this is +2 and this is -1, right? Nitrate's -1. So how many nitrates do we need? 2. I'll put aqueous there as well. But we already knew we needed 2 because I put this 2 in front of the HNO3. So that's implicit from that is you got 2 H pluses and 2 NO3 minus. So there's our balanced equation. And there you go. Okay. So there's that type of problem. That's a fun type of problem. I like that. That's real chemistry writing, chemical equations. Okay. Let's see what else we have here. Okay, I'm going to do this one right here. It's kind of a checkbox type of problem, checking what kind of reactions we have here. We're putting together different types of reactions here. So some of this is from chapter 3. The end of chapter 3 discusses types of reactions. So I just want to point that out here. So one thing to be careful with this is make sure that you check all that apply. So sometimes more than one type of reaction. So let's take a look at this one right here. This is an example of the precipitation reaction that we looked at in the earlier section, 4.1 and 4.2. Metal, non-metal, metal, non-metal, right? Aqueous, aqueous, product, metal, non-metal, aqueous, metal, non-metal, solid, right? Aqueous plus aqueous gives you aqueous plus solid. That's a precipitation reaction. So this one is precipitation. But it's also, just like the acid base, binary ionic compound, metal with a non-metal, binary ionic, metal with a non-metal, binary ionic. Two parts, switching partners. The copper was originally with the sulfate. Now the copper is with the chromate. The zinc was originally with the chromate, but now the zinc is with the sulfate. So that is also not just a precipitation, it's a double replacement reaction. So both of those are true. This one looks like an acid base, right? They just wrote the base first, right? So KOH is one of our ionic bases. HBr4, that's one of our oxo acids. That's an acid base reaction. So it's a double replacement and an acid base. Third one, NaOH, ionic compound, HBRO. Oh, that's an acid. So this is our acid-base reaction. So again, double replacement and acid base. Now take a look at this one. This one I didn't really talk about in great detail in chapter 3, but it's in there. It's in some of the discussions. When you have an organic substance, and an organic substance is a substance that has carbon and hydrogen. It can have other elements too, but if it has carbon and hydrogen, it is an organic substance. Reacting with oxygen to form carbon dioxide and water, that is called a combustion reaction. So that's one you need to know. Combustion reaction is where an organic compound, something with hydrogen and carbon and maybe other elements, is reacting with O2 to form CO2 and water. You may have other products as well, but if you have the CO2 in the water and you have the organic substance and the oxygen, that is definitely a combustion reaction. Okay. Take a look. There we go. Got another problem here. Identifying acids and bases by their reaction with water. Remember we talked about that, how an acid reacts with water to form hydronium ion, H3O+. A base reacts with water to form the hydroxide ion, OH-, which were the nitrogen bases. So imagine a little bit of these compounds. So these ones over here are put into water, so one at a time. What's going to happen? Are you going to have ionic compounds? It even tells you what the products are, okay? So now there's one aspect that I haven't really discussed much about, which is the strong, weak aspect of it. The nitrogen bases only form a small amount of hydroxide, so they're called weak bases. The metal hydroxide compounds form a lot of hydroxide, so they're called strong bases, okay? So nitrogen bases are weak bases. The metal hydroxide bases are the strong bases. In terms of the acids, organic acids are weak, and the inorganic acids are generally very strong, although that's a little bit complicated. Some of them are strong and some of them are weak. So what I'll do is I'm going to give you a list of the strong acids. If it's an acid, but it's not one of those strong ones, we consider it weak. So here we go, CH3NH2, that's a base, right? That's a nitrogen base. I said if the compound has nitrogen and hydrogen or carbon, then it's a base. So that's a molecular base. But again, the nitrogen bases are weak. So it's a weak base and a molecular compound. Second one, sodium bromate. Well, that's not an acid or a base. It doesn't have the hydroxide. It has the sodium. That means it's ionic. So that is just an ionic substance. This one, This one, I didn't show it to you, this one, but it tells you, take a look at what you got here, H3O plus. That's telling you it's an acid. If you put this into water and you get H3O plus, that means it's an acid, just like this one at the top. If you put this into water and you get OH minus, that tells you it's a base. Look at the second one, no H3O plus, no OH minus. It's not an acid or a base. That's why it's just ionic. So this one's definitely an acid. It's molecular because there's no metals in there, so it's a molecular compound. But is it strong or weak? Well, you can't tell from this part right here, but organic acids are always weak. So that's a weak acid. Okay, molecular and weak. This one is going to be sodium hydroxide. So that's one of your bases. It tells you it has OH minus, so you know it's a base. We said earlier those are ionic, but I'm also going to tell you that they are strong with the exception of magnesium, right? Magnesium hydroxide. So I would make a list of the strong acids and the strong bases. And just to help you, I'm going to list the strong acids and strong bases here, and you can put them on a little piece of paper. So here's a list of the strong acids. Okay. HCl, HBr, HI, those three. HNO3, H2SO4, HClO4, HClO3. These two are very similar, just 4 or 3. Those are your strong acids. Any other acid, so remember, if it said H3O plus was produced, then you know it's an acid. But if you don't know if it's strong or weak, those are your strong right there. Anything that's not in that group would be weak. So this is going to be a much larger list, right? So that HC2H3O2, that's going to be weak. HF is going to be weak. HNO2 is going to be weak. H2SO3 is going to be weak. There's going to be a much bigger list of weak acids. So we don't memorize those. We just memorize the strong acids. So make a list of the strong acids for yourself. Strong bases. Not many of them. Lithium, sodium, potassium, rubidium, cesium, all with a hydroxide. Okay. Then you get your calcium, strontium, and barium. Okay, so it looks like there's 8, right? 5 and 3 is 8. Here it looks like we've got 7, right? So 1, 2, 3, 4, 5, 6, 7, 8. Here you got 7. Okay. All others are weak. They don't form very much hydroxide, just a little bit. Okay, that's why you can put some bases in your water. So what do they call those bath salts? You can, they're basic actually. They make the water a little basic, a little alkaline, high pH. Sometimes they call that. Not very much though, so it's not damaging to your skin. Okay, so examples: all the nitrogen bases are weak. Okay, and then we also had magnesium hydroxide, that one. So it'd be interesting to see if Alex gives you that one. Okay, so there's your issue of strong and weak. And now I just want to briefly mention this last one. So let me show this one up. Kind of rip through these just to give you, but again, there's more videos that I posted this week for this topic. Predicting the products here. Now this one is also acid-base reaction, but notice it's a reaction with water. So it says predict the products, and these are all predicting it when you react with water. Again, you're going to show the products right here, the state symbols, aqueous or liquid, that kind of stuff. So here's what you do. First of all, you recognize this is an acid, and they're telling you it's a strong acid reacting with water. So here's the way you approach it. If this is an acid and it's reacting with water, that tells you water's got to be the base. That's what it's essentially saying, is that an acid reacts with water. That's one way to think of what an acid is. It's something that reacts with water and donates the H plus to the water, transfers an H plus to water. So let me show you this one, and then we'll be done for this section. Tomorrow, I'll start working on redox reactions. Here's how you approach this. It tells you complete the equation of a strong acid. So we know this is an acid, so that means this has got to be a base. The acid donates the H plus to the base. Okay, so now if you take the H plus, let's come back to what we mean by that. Right? Again, remember you can think of water as H plus and OH minus. Switch partners is essentially what you're doing, but in this, it's a little bit different. What you're doing is you're donating the H plus here to the water. So now that water is going to be two H pluses. So it's H, H, and then this H, three H's. But it's also a plus that you're adding. You're adding this plus, so it's plus. Again, ions are written as aqueous. And then the NO3 minus has lost the H plus. So that's a little bit different than the double displacement, right? Or double replacement. Okay, ions are aqueous. Is that we're not double replacement. What we're doing is we're just transferring the H plus to the base. Okay, so this H plus goes into the water. This is already H2O. So you get your famous hydronium ion. Okay, and just to sum up, sometimes people will write this. Put it in water. It just dissolves into two ions, forms the hydrogen ion. Okay. That's called the Arrhenius model. But here's the other approach. HNO3 is actually reacting with the water, donating or transferring the H plus to the water. And there you go. So same equation, I mean, the same process. This is just called Bronsted-Lowry. You'll see that term out there. But it's showing us that this is going to make the water acidic, right? If you have this in water or this, it's going to be acidic. The water will be acidic. Okay. So good luck with all of this. And again, like I said, tomorrow I'll start working on the next section, which is redox, oxidation reduction reactions 4.3. And feel free to watch this video, but also the previous ones that I've already posted in Blackboard. So take care.